Section 4.4 is about concavity and curve sketching. Now in this section actually we are going to build up our skills, and then we are going to learn about concavity, which is going to be a great help, and which is going to help us to do the curve sketching on our own. That's the goal. That's the goal in this section. So what is concavity then? We need to understand. Okay, concave down, it's the graph. When the graph is going to looking like this. Okay, actually, in order to have a concave down, first derivative, the slope is decreasing. Look, if you start here, the slope of this tangent line is big. If you get as x increases, you have a tangent line going like this, and the slope is decreasing. Okay, for concave up, on the other hand, the slopes are getting bigger. So look at, take a tangent line here, it is this. Take another one, it is this. Take another one, it is this tangent line. And then take another one here, it is this big tangent line. The slope is bigger, getting bigger. That means f prime is increasing, the derivative is increasing. Derivative is increasing means derivative is the slope, right? Slope is increasing. Whenever slope is increasing, slope of the tangent lines are increasing, we have concave up. Whenever the slope of the tangent lines are decreasing, we have concave down. So this helps us to draw the graphs easily. So in this case, between 0 and between negative infinity to 0 on this part, the graph is concave down. After 0, the graph is concave up. All right, that's what the concavity is. It is related to the slope. Okay, slope being increasing or decreasing. So this slope is important. Next, we are going to give a definition, a formal definition. So we are going to start with a function that's differentiable function. We are going to say, okay, the graph of a differentiable function is concave up on an open interval if the first derivative is increasing on I. In other words, the slopes of the tangent lines are are getting bigger. And we are going to say the graph of a differentiable function y is equal to f of x is concave down on an open interval I if the first derivative is decreasing on I. In other words, slopes of the tangent lines are getting smaller. Okay, which is the same as first derivative being decreasing, getting smaller and smaller. Okay, in the previous section we learned about the first derivative test. Now in section 4.4 we have a second derivative test, and this second derivative test is about the concavity. So this second derivative test is going to tell us when the graph of the function f of x is concave up or down. Okay, it's going to tell us that. So how do we do that? So we take f, we take the second derivative. If the second derivative is greater than 0 on the interval that we started with the interval I, then the graph of f is going to be concave up over that interval I. If, on the other hand, the second derivative is negative on that interval for each x, the graph of f is over this interval I is concave down. So this is very simple way to check to see f being concave up or the graph is concave up or down. So that's why it's called the second derivative test for concavity. So you use the second derivative to see where the graph of the function is concave up or down. Okay. Let's consider, this is an example 1b in our book. Let's consider the graph y is equal to x squared is, you would see, excuse me, you take the second derivative of x squared. So first derivative is 2x, second derivative is 2. Right? So the second derivative is greater than 0 whenever x is less than 0 and whenever x is bigger than 0. That would mean, excuse me, that the graph of f, alright, so what I meant is the second derivative is 2 everywhere. So that would mean by the second derivative test for concavity, the graph of f is going to be concave up everywhere. So it's concave up here and concave up here, okay, because of that. So let's consider this is example 2 in our book. Let's consider the function y is equal to 3 plus sine x, and the blue one is the 3 plus sine x. Let's take the second derivative of this. Take the first derivative, you get cosine x. Take the second derivative, you get negative sine x. Look at the negative sine x. This is the graph of the second derivative. Okay, it's okay, as you would see, second derivative is going to be negative between 0 to pi, and it's going to be positive between 0 to pi to 2 pi. So that would mean if the second derivative is positive here, negative here, then the graph of f is going to be concave down, and after pi it's going to be concave up because the second derivative is positive. Alright, then it's going to be negative again, so it's going to become concave down again. Okay, that's very good. Okay, next we have another terminology. So far we talked about the critical point, we talked about the first derivative test, second derivative test. Now we have a point of inflection. This is also very important to draw a graph. Okay, so what's the point of inflection? Okay, there are some points on the graph such that at that point we have a tangent line, and also at that point we have the concavity changes. So before this point, concavity, we might have concave up, and after this point we may have concave down for the graph. Then this point is actually a special point which is called point of inflection. So we, again, for the point of inflection, we require that C is a point of inflection, or C comma f of C is a point of inflection if at that point C f is at that point C f of C we have a tangent line, and also we have the concavity changing around that point. Okay, okay, and we have a note here. At that point of inflection, we are going to have either second derivative is 0 or second derivative at that point fails to exist. So we may have one of the two. Let's see the example. Let's say this is the function x cubed y is equal to x cubed minus 3x squared plus 2. And if you look at this graph, let's try and see the graph first. Okay, so we have this concave down here before 1, and after 1 we have concave up here. Okay, so 1 is a point of inflection. Okay, okay, let's see another one. Alright, so this is another example. This is example 4. Y is equal to x to the 5 over 3. You can take the derivative of this 5 over 3 x to the 2/3, and then if you take one more time, 5 over 3 times 2/3 times x to the negative 1 over 3. Okay, that's the second derivative. Okay, whenever x is positive, it is positive. Whenever x is negative, it's negative. So before 0, it's concave down. After 0, this is concave up, and concavity changes at 0. Okay, but second derivative at 0 doesn't exist here. Why? Because f second derivative of f x is like 1 over x to the 1 over 3 times a constant. So at 0, it's in the denominator, it makes it undefined. So here we have a point of inflection where the second derivative is undefined at 0 at that point of inflection. This is an example. In the other previous one, if you take the derivative twice, you get 3x squared minus 6x and 6x minus 6. 6x minus 6, x is equal to 1. Okay, x is equal to 1, x is equal to 1, second derivative is not 1 is where the second derivative is 0. So this is an example where the second derivative is 0 at that point of inflection 1, And the next example, which is example 4, we found a point of inflection where the second derivative fails to exist at 0. So as we said here, a point of inflection, CF of C, either f double prime C is equal to 0 or f double prime C fails to exist. So we have one of the conditions, one of the things happening. Okay, so this is an example where there is no point of inflection or inflection point. Let's check it out. So this is y, which is x to the 4. Take the first derivative, you get 4x cubed. Take the derivative one more time, you get 12x squared. If you equate it to 0, you get 0. So second derivative becomes 0 at 0. However, this is not a point of inflection. The reason is before 0 it is concave up, after 0 it is concave up. Concavity didn't change. So there's no way 0 is a point of inflection. Here's an example where we are going to have a point of inflection at 0. However, y prime and y double prime fail to exist. Let's check it out. Okay, y is equal to x to 1/3. Take the first derivative, you get 1/3, x to the negative 2/3. So you get 0. If at 0, the denominator makes the denominator 0. So first derivative is undefined at 0. So that's why it doesn't exist. First derivative doesn't exist at 0. And the second derivative is similarly, if you take the second derivative, you are going to get some x terms in the denominator. That's going to make the denominator 0. And second derivative is undefined at 0 as well. So for the point of it is still a point of inflection. The reason is before 0 it is concave up, and after 0 it is concave down. So concavity changes, so it's a point of inflection. That's very nice. Okay, what is this? I think these are the graphs. Which example are they? Let me check it out, okay? Just a